2.18. Consider the temperature distributions associated with a dx differential control volume within the one-dimensional plane walls shown below. So we got 4 schematics being shown, and for each one they're asking questions. So for part A schematic, it says steady state conditions exist. Is thermal energy being generated within the differential control volume? If so, is the generation rate positive or negative? Part B is the same question as A. It's just a different schematic. Part C is steady state conditions do not exist. There's no volumetric thermal energy generation. Is the temperature of the material in the differential control volume increasing or decreasing with time? And then part D is the same question as C. It's just a different schematic. All right. So we have a dx differential control volume. And then it has one-dimensional plane walls. So 1D plane walls for all these. And then they want us to find, for part A, it's steady state, and they want us to find is thermal energy generation. So is there thermal energy generation? And then is the generation positive or negative? Okay, part B is the same as A. So it'll just have a different schematic. C is now steady state conditions do not exist, so it's transient. And no generation, so no thermal energy generation. And it wants to know, is the temperature of the material in the differential control volume increasing or decreasing with time? So is temperature increasing or decreasing with time? And then D is the same as C. All right, so now we got a bunch of schematics to draw. Oh, let me, this is, right, and then our temperature distributions in these. Nope, that's even worse. All right. There we go. That's good. All right. Don't touch it. All right. So we have our temperature distribution for part A. Part B, nailed it. All right. We have another one. All right. We got two more schematics to draw. That's good. All right, so we got these four schematics, and they got different kind of questions. A and B are asking kind of the same question to those problems, and then C and D are asking the same thing to those two schematics. So for part A, we have steady state, right? And it wants us to figure out, is there thermal energy generation, and then is that positive or negative, that energy generation? Okay, so where do we begin?
Already got the energy equation or conservation of energy.
Conservation energy, okay. All right, and then for part A, it says it's steady state, right? So that just gets you this, okay? So we're ultimately trying to find this, or an understanding of it, that energy generation term. So then how do we get an understanding of energy in and energy out then?
So is there a vertical axis that's temperature?
Yeah, so it's
Okay.
basically temperature. Yep.
Oh, so we could just analyze to see like where we're starting off temperature wise on the vertical scale and where we're ending on the other side of the dx.
Okay. Yes. So we have the temperature. So we see it's going up. So what does that tell us? From the left side to the right side of dx.
So there's more energy coming in than energy going out.
Maybe. So temperature by itself. Oop, there's another comment.
I was just saying it's increasing over time.
Over time. So it's steady state. So it's not, there's no time in this one. So let's go back to how did we get E in and E out, right? So this is where we can look at Fourier's law. So let me draw it in a different color here. In Fourier's law, because we're looking for energy in and energy out. It does use temperature, but what does it use with temperature?
The position or distance.
It uses the position.
Change in position.
Yeah, different change in position, change in temperature, which is the slope, right? So that would be, if we're looking at the right side, that would be our slope there. And the left side would be our slope there. So first off, which way is heat flowing through this dx control volume? Is it going from left to right or right to left?
Right to left.
Yeah, so we have high temperature on the right, low temperature on the left. We know it's flowing in that direction, right? That means this is in and this is out of our control volume. Okay, the right side is in, the left side is out in this problem. The other way, we see high temperature to low temperature, which also we could see from just looking at, if we look at our dt dx being our slope is a positive slope, right? And in and out. So we have a positive slope here. So we'll end up with negative. So that'll give us the negative direction. So that's from right to left, because our positive direction is from left to right. Okay, so that also tells us we're going from right to left here. Okay, all right. So how do we get then energy in and energy out then? Is what I labeled here is the heat flux in different than the heat flux out on our dx control volume? Are the slopes the same or different?
No, they're changing.
So the slope is different, all right? So which has a greater slope?
Heat
Looks
flux
like in.
Yeah, in is going to have a greater slope. So that'll mean dt dx is greater for heat in. Okay, so that means we're going to have then let's write the next step. Okay, so if we said the slope is greater for the right side, does that mean the heat flux in is greater than the heat flux out, or less than? Is the heat flux in greater than the heat flux out, or is the heat flux out greater than the heat flux in?
Heat flux in is greater than heat flux out.
All right, so we have then so what does that tell us about energy generated? Is there energy generated?
No.
Does everyone agree with that? Okay, so if in is greater than out, so then this quantity is greater than this quantity. That means for this to be equal to 0, that means there has to be some energy generated, right? For this whole equation to be equal to 0, that means for there to be an energy generated equal to 0, the flux in is to equal the flux out. So that would be a constant slope here. The slope on the left would be equal to the slope on the right, would be where there would be no generation. Okay.
So then the energy generation will be negative.
Yeah, so there you go. So then the positive or negative question, so we're putting in more in and we're only getting some out on the surface. That means the generation term has to take the rest. So the energy generation is greater than 0, or less than 0.
Yeah, that's where I got confused. I thought energy generated was only positive for some reason. But that makes
Okay.
sense.
Yeah, so this could be an endothermic reaction or something like, so it can be in the opposite direction. Yeah. All right. Part B is the same question as A. It's just a different schematic, right? So we'll walk through it again. Which direction is the heat flowing? Is this going from left to right or right to left?
Right to left.
Right to left still. Okay. And then we got, we can check that again. Okay, so then we have our still positive slopes, right? So we get a negative direction. All right, so we have our COE equation for part B, and we start labeling. This is our heat flux in, and this is out, right?
So this time we're going to have more heat flux out than in, right?
Correct. Okay, so from that higher slope for out, that means out is greater than in, which what does that mean for energy generated?
Positive.
Yeah, so our energy generated greater than 0 in this case. Again, if the slope was the same, we just had like a, a constant slope throughout that dx, we would have no energy generated, right? Because the heat flux in would be the same as the heat flux out through that solid surface, through that solid. All right, part C. So if we go back to our COE, so part C, it's transient, no thermal, so transient, no thermal generation, thermal energy generation is the temperature inside the control volume increasing or decreasing with time, okay? All right, so if we start back at our COE, there's no energy generated, but we have energy stored, okay? So we have now,
Professor, I must have forgotten, but transient just means energy generated is 0, right? Is that it?
no, this transient means there's changed energy stored part.
Okay.
So this right here, all right, so this is our generated term. This is our stored, right? So this goes to 0. The stored term goes to 0 when it's steady state. It's not changing with time.
Right.
All right. So remove the energy generated term, and now we have the energy stored term that's changing with respect to time here. Okay. So let's walk through this again. Which direction is the heat flux flowing? Left to right or right to left?
Left to right.
Okay, so we have heat flux going from left to right. And if we look at our slopes again, right? So we can check this again. We have negative, and then our slopes are negative, right? So that gives us a positive. So positive direction. Okay. All right, so then we label again. So that means this is the left side is in, and the right side is out, okay? Which one's greater? In, okay? So we have a steeper slope, so it's gonna have more heat flux going in than going out, okay? So we say in is greater than out, right? So what does that tell us about the question? Is temperature increasing or decreasing with time within our control volume?
Decrease.
What was
It's
that?
increasing.
Okay. So yeah, so in is greater than out. So then we're going to be left with positive energy stored DEDT. So that means we're putting energy into the control volume, which would increase the temperature. With respect to time. Okay. All right, part D. Which direction is heat flowing?
Left to
Left left to right. Okay. Check it again.
So this check that you're doing is to verify that the line is moving in the positive X direction.
Yeah, it's kind of another method just by the math to determine the direction. Right? So I'm showing it intuitively. We know it's going from left to right by looking at the temperature, but I also like to show it with the math, so then we know, what it means by the math term of where it's going, positive or negative too. Okay, so to kind of correlate the two together. All right, so then we can rewrite this, and we have, means we have in the left, and out on the right. So which is greater?
Out is greater than in.
Yeah, the out is greater than the in. So we have so that means we get a negative. Okay. And our temperature is decreasing with respect to time. Okay. Any questions? All right, so this is a good question on kind of understanding Fourier's law and how that tells us about energy in and energy out, heat flux, and goes right, kind of correlates with what you could do with the heat equation. Okay. So the other thing we saw, right, I'll bring it back, is we saw with the heat equation when it was steady state, it looks like this. And if you integrate twice, you get this line, right? So if it's steady state and you get a line, right, that means you don't have any energy generation terms. So we had a curve here, steady state, energy generation. So if we have the version with energy generation, so here's our equation that we derived last class, and we do 1D steady state, we're going to get right, so this is again steady state, right? So the right side is gone. So this is our heat equation, 1D steady state, 1D heat equation of constant properties. All right, so if we now integrated that twice, we get something like this, okay? So with that one, it has energy generated, thermal energy generated, and now we, in a steady state, okay, 1D, and we see we have this additional term, which has x squared, right? So if we went up back to our A and B, we could see they're curved, right? So that has that second order curve to it, has energy generated, okay? And we could also use them. So it's another kind of process to figure out what the energy generation, whether there's energy generation or not. Just by looking at that curve, we can kind of, from the math, we can just tell whether there's energy generated or not too, not just conservation energy. We can use the heat equation. All right, so that's it. We'll probably do at least one more problem next class, depending on how long it takes, maybe two. And then we'll be on to 3. Okay. Questions? This is where stop here, unless you have any other questions. Ooh, internet's not doing well. Anyways, I'll let you go. Have a good rest of your afternoon here, or evening, getting close to. And I'll see you on Monday. All right.
Thank you.
Thank you, Professor.